So guys, girls, I've got an ATX power supply here, another one. This is absolutely filthy. I mean, this is supposed to be the ventilation slot. It's like absolutely clogged up with dust and dirt. It's quite an old one, I think. It's a 400 watt. It's a 400 watt ATX. So I've got this little tester that I bought, analyzer, yeah. Power supply analyzer. Basically, it just monitors the voltages. It doesn't do anything you couldn't really do with a multimeter, but it's quite handy. It was only €9 something, less than €10. So I thought it was worth having. I made a video reviewing this. You might have watched. I'll have to link it onto this one. So I've connected the power supply tester to 12 volts into the ATX. I mean, I could also connect the Molex into here, or if it had SATA, it could go in there. But I think that's really just a meter, so it doesn't actually put a load on the power supply. So I like to give them a bit of a load. They work better with some sort of load. So this is an old ID hard drive, which I can use for testing. Really, I'm not going to use as a hard drive. It's just something to draw a bit of power. Yeah. So I plug the 12 volts, 5 volts into that, and the power supply. I've got the mains lead connected to this limiter here. So when it's on limit, it powers the power supply from the mains via the light bulb. So the neutral goes straight to here, and the live goes through the bulb to here. And that's just to see if it draws any current. If it comes on, there's a short. All the usual stuff. I've mentioned this before. I'm expecting this to pulse and go off, but I think this one's dead, so I think it does nothing. So let's just switch the power on, yeah? Yeah, power's on, and absolutely nothing at all happens, yeah? Nothing at all. Doesn't matter if it's live or limit off or nothing. So this appears to be completely open circuit. Yeah, it's drawing absolutely no power whatsoever. So we need to have a look and see what's wrong with this one. Oh, I've just dropped. I have two light bulbs on this. I have a 60 watt and a 100 watt. So I have an option of you know, setting effectively the current limit 60 watt, 100 watt, or 160 watt. But for small things, 60 is fine. Okay, so let's disconnect all this for now. We don't need that. And let's have a look to see what the situation is with this power supply. So the first thing I'll do is disconnect everything and open it up. Yeah, let's have a look to see what we've actually got inside this one. As usual, 4 screws, nothing very complex on these things. Nothing very difficult to take these apart. This is a 20 pin or a 24 pin. It has like a little thing with the extra 4 pins on, yeah. It's not very valuable, but you know, all these repairs are interesting because we learn something. Yeah, we learn things. Yeah. Let me just move this. There you go. Yeah, I talk to you now. Yeah. So yeah, knowledge is everything in this game. So really, when you're learning, you should be trying to fix everything like you can get your hands on, regardless of whether it's really worth it. You can judge whether it's worth paying the price. So the lid's off. It's very dirty. You can see that. And the first thing I see in this one, apart from the fact it's completely gummed up with dirt, is that there's a capacitor. Yeah, this is an exploded. This is the lid off a capacitor. It's the top end of a capacitor. So something's seriously gone bang in here. Yeah? I can't see immediately. Oh, I can see where it's come from. I can see. Let me just zoom it in a little bit. Oh dear. Oh dear. This is gone bang seriously down here. Okay. It might not be worth fixing, but it's got to be worth taking this apart to see what actually happened here. Yeah, it looks a bit catastrophic, doesn't it? That, to be quite honest. I'm guessing there's a fuse. Yeah. There's a fuse there, so the fuse is obviously exploded. Okay, let's take it apart. I'll just pause the video and I'll show you when I've got the circuit board out of it. So I've taken the screws out, so the circuit board's loose now. I've just got this like this. I want to just discuss something with you that's very important. Yeah. So these are the main capacitors, and these can hold a very high voltage. Yeah, 300 volts or so. and they're large enough value to give you a very nasty shock. And quite often, when the thing's been switched off for some time, yeah, if like this part of the circuit's open circuit, the main switching transistors or something, then these can hold a very high charge, yeah. In this case, we know they haven't, and the reason being that when we switched it on with the light bulb, there wasn't a pulse, there wasn't like a flash, so we know no power's going in. Plus, we know the fuse has gone bang, yeah. So we know these are not live. But you notice at the moment I've got no power plugged in, yeah, obviously. Now, what I want to show you is this. Down here is the switch. Yeah, this is the switch, on, off. Okay. Now that's a single pole switch. Yeah. So it switches, you would assume, the live. So this is designed such that when you plug a power lead in here, the live is on this pin, yeah. So this disconnects the live, yeah. So when you switched off, you've only got neutral in here and not live, so it should be safe. I mean, this heatsink is quite possibly live when the thing's switched on, or neutral, yeah. But what you've got to be aware, especially in the EU where we live in Europe, our mains plugs, as you'll know if you live here, and I'll show you if you don't, these are our mains plugs, yeah. And you've got two pins, and you can put them into the sockets either way round, yeah. You can put it in one way or the other way. So depending on which way you plug this in, yeah, or whether you've got a plug like this and somebody's wired it up right or wrongly, or the power socket in the wall is wired up right or wrongly, it's possible that this switch is switching the neutral and not the live. Okay. So from a point of view of switching it on and off, it doesn't matter. It doesn't matter if you break the neutral, you break the live. It still switches it off, yeah? But you can't trust it to keep you safe. So if you've got the power lead, effectively, you've got power plugged into the back of here, yeah? Okay, and you want to work on it. It's plugged into the wall socket. So you're switching the switch off and you think, switch a switch off, it's safe. It might not be. You may have just switched the neutral off now. Yeah? Obviously, more so in like Europe where we have these two-prong plugs, and anywhere else in the world we have these sort of things. So you've just switched the neutral off now, yeah? Live is still here, yeah? So what's going to happen when you touch it? Yeah, okay. I don't mean to lecture, but that's an important point, yeah? Never trust the single pole on-off switch here to be breaking the live, yeah? Always unplug it before you open it up, okay? Lecture from Richie, but there you go. I hope you understand the importance of that, yeah? So, here's the PCB can come out. It looks like a bit burned underneath as well. Yeah, into the view, yeah. Can you see it? No? Something getting hot. Let me zoom the camera out a little bit. There, you can see it a bit better now. So, we've got the circuit board coming out. I'll have to switch the soldering iron on now, because I need to desolder the power lines coming in, live and neutral, yeah. I'm just trying to decide if it's easy to desolder the wires from the switch or from the board. I think I'll desolder it from yeah, good question. This one's not going to be easy to unsolder from here. I'll unsolder it from up here. Oh, that's the how many wires are there? There's 3 wires, and the reason there's 3 wires is this thing is designed to work on 110 or 240 volt, yeah? So there's 3 wires, and we've got to know which one goes where. That's the important thing with this. So this one here is on the middle of the switch down here, and I'm going to put a blue mark on it, yeah? So I know that that one goes to the middle of this voltage selector switch. And what I'm going to do is now I'm going to cut them. I'm going to cut them off and then resolder them back on afterwards. So that's the switch. Yeah, this is this end of the voltage selector. It's easier to do this and resolder them on than just try to unsolder them, I'll tell you. It's no hassle, yeah. So we have 2 there going to the switch, and we have another one. We have another one. Trying to think which way that switch is. Yeah. Those 2 we're open when the switch is on 240 volts, so we don't need to connect those together to test it. We do need to connect this one, and we need to know now which this one is to solder it back on. Let's put a mark on that one. Black mark, yeah. While we're at it, because sometimes we'll do this and forget what we were doing. Yeah, put a blue mark on the one where the blue mark goes. Yeah, right, now we've got it. Okay, and it's now held on by the fan. This, I think I might just desolder this one actually. I've chopped enough wires. Again, the red black already marked on the connector. Yeah, it says ground on the black one. That's enough for me. Black says G and D. That's good enough for me. Yeah, I can live with that. Okay. So there's our PCB. Yeah, this is absolutely filthy. I won't bother cleaning this up yet, in case we decide it's not worth fixing this yet. If we want to fix it, want to clean it, we can clean it. I mean, look at the state of this. Just look at the state of this thing, yeah. So we can't do anything with this until we've actually got it clean, yeah. So I'll just get it over the dustbin and brush all this dust off it. Okay, so I've cleaned it up. So what have we got and what's really happened with this? Well, we can see. Let's drop me wire cutters. Fuse is blown, yeah. But what we have here, we have the fuse. So your power comes in here on this one and this one, yeah. These two go to the voltage selector switch, 220, 110. And I've just looked at the switch, and when these are not connected together, that's 220. We have 220, so I can test this just by putting power on these if I so want to. So power coming in. This is a bridge rectifier. So you have 4 diodes. So let me zoom down on it a little bit. So yeah, this is a bridge rectifier here. So we have 4 diodes. Yeah, AC comes in and DC is going out. And the DC is going to these 2 capacitors, yeah, which are in series. Down here we have 3 big transistors. These 2 will be driving the main power transformer, this one, yeah, and this one generates the 3 volts, the 5 volts and the 12 volts, yeah. And so this transformer will have a number of different secondaries, yeah, for the different voltages, 3, 5, 12, minus 12. And down here, on here, where it's still a bit grubby, need a cleaning here. These are the rectifier diodes, 1, 2, 3 big ones. So that'll be 3, 5, and 12, and then probably be a small one somewhere down here that does the minus 12, because the minus 12 only supplies a very low amount of power. In fact, some ATX don't even have the minus 12. Okay. The purple one is your 5 volt standby. And the green one is the signal which comes back to switch the main power supply on. This 3rd transistor here, yeah, this will be driving this transformer. So this is your startup. This is your standby power supply, yeah. And that diode there, which is close to this transformer, that will feed to the 5 volt standby, and we can check that quite easily. If we just get the voltmeter, yeah, switch on to ohms range, put it somewhere where you can see it, yeah, and we go to this diode here, yeah, and we find the purple wire in the ATX, yeah, so there's your purple wire there, yeah, and we come to this diode, yeah, so that diode is generating your 5 volt standby, okay. Down by the diode generating that is a capacitor that has exploded. This is the remains of a capacitor, and this is the lid. And the lid says this was a 47 microfarad 50 volt capacitor. So it's a fairly high voltage one, yeah. And that's gone with some bang, which either suggests there's got a lot of voltage coming here, or the capacitor itself has failed, dried up and exploded, yeah. But effectively become like leaky like a resistance and overheated and gone bang. So we don't know exactly which. Okay, but we'll find out. So this standby power supply here generates the 5-volt standby and powers this chip. Okay, this chip is controlled by the signal on this green wire. So when this green wire has 0 volts, it switches that on. That's how the motherboard switches this chip on. This starts to oscillate, and then via this transformer it drives the mains transistors over here. Okay, so if you look here, there's a big gap on the circuit board, yeah, down here, yeah, there's nothing there, a big gap, yeah. The only thing bridging the gap are the transformers, yeah, transformer, and the little transformer. Yeah, there's 2 here, yeah, 2 transformers, the big one, and then the opto isolator, which is here. Okay, this thing. So this side is completely isolated from this side. This side has ground, yeah, safety ground. This side has no safety ground. It has what's called hot ground, yeah. The negative end of the bridge rectifier, the negative end of these two, one of these capacitors are in series, is what's called hot ground. So it's a ground reference for this for high voltage, but it's not connecting to ground safety ground. In fact, because the bridge rectifier, on one half cycle of the waveform, say the negative half cycle, the ground here is connected to neutral, and on the positive half cycle it's connected to live. It's floating. They used to call this half mains potential. What they actually meant was all of the mains potential half of the time, yeah. As you find out when you touch it. So that's how it should work. What's gone wrong with it? Well, this is exploded. That's the first thing I can see. Why did it explode? Well, we need to check a few things to see now. Obviously the fuse is gone, so a lot of power's gone here somewhere. So the first thing I want to check is on the outputs, yeah, because I just happen to have the ATX connector in my hand. So I want to see whether there's any short circuits on the output of this, yeah. I might see some resistances, but we can hardly any shorts. Well, that's 12 volts and that's not short. Let's go to a red one. Wire in. Let's put the black in here. Right, black's in ground again, yeah. Let's go to one of the red ones. This is 5 volts. No, that's 50 ohms, that's fine. Orange one is 3.3. That's 26 ohms, that's fine. Grey I think is minus 12, there's nothing on there. Standby, 50 ohms, yeah, purple. Green, which is the power supply on. So there's no short circuits on the output of it. So that isn't what's caused the problem. All these output capacitors, these look okay. They look okay, I'm not saying they are okay, they look okay. Let's see if we get any short circuits on this side. So these are your main switching transistors, yeah. One's there, 3 pins. The other one I'm guessing is here. I see 3 pins in a row. Yeah, just sprayed out 1, 2, 3. Second one's there, and then the other one is here. 1, 2, 3. So these two are the main power supply. 3 volts to 5 volts to 12, and this is a standby. So I want to see if there's any short circuits here as well. Do I see anything? I might put it onto diode test mode. So if I see any diode junctions. So one end will be the base. That's reading like a short. That's reading okay. That's reading okay. These two are reading like a short. So we need to look at that device. We need to take that out and see what the problem is there, yeah? This is the one that drives the standby voltage. So look at the other ones, the main ones. Yeah, that was looking quite low as well. Yeah, so we need to take these out. That sort of looks better. Yeah. So this one and this one have some very low resistances around them, so that's something we need to take out, yeah? We also need to remove the remains of this capacitor, because this could well be short circuit anyway, yeah? Do we have any short where the fuse is? It's another good question. So fuse coming in, yeah. One end of the fuse I think goes to this black wire. Yeah. So the other end of the fuse should go to the bridge rectifiers. Yeah, this end of this fuse here. Yeah. Should go to the bridge rectifier somewhere. These two, but it's not just the one. Oh yes, that's strange. Should go to 2. No, it should go to that one, and yes, and then it should go to the negative of this one. Yeah. So that goes to there. Is there a short from there to the other two? No. Let me show you that on a bit of paper, what I've just done, so it doesn't confuse you, yeah? Let me get a piece of paper. Okay, what I was just doing. Bridge rectifier has 4 diodes, okay? Like this. Okay? And then the other one. And the other one, yeah? Just remember putting the right way around. Okay. And this is plus, and this is minus, and these two are AC, yeah? And our fuse is connected to one of these, yeah? And what I was checking is, from, obviously this is gone, yeah? But from the fuse it should go to 2 ends of these diodes. So like there should be 2 diodes connecting to there, yeah? And that's what I was looking for. So the 2 diodes connecting to that fuse, there's a fuse, yeah? Get my voltmeter in again. So to the fuse goes to that one and that one. So that's this point, okay? And what I wanted to know is there a short from there to neutral, okay? So basically I was going from the fuse. I know it goes to 2 of these, yeah? And I wanted to know, was it shorting to the other ones? And no, it isn't, okay? So I know I haven't got a short circuit across the live to neutral, okay? We can double check that anyway as well, because we can look at these 2 big capacitors here, yeah? On the input. One of them's here. We can check it for shorts, no, it's okay. And one of them's here, we can check it for shorts, it's okay, and we can go across the whole lot and it's okay, yeah, no shorts. So there's no shorts on the input. We've got some suspicious looking transistors, so this needs to come off and we need to test those, and we need to take out this exploded capacitor, and then we need to have another loop to see what we've got. So next thing will be to get the soldering iron ready and do that. So we know we have some low resistances around these main switching transistors, and the one that drives the 5V standby as well. I will mention, as I already pointed out, and if you think about it you might already have worked this out, this transformer is being driven by this chip, and it drives the base of the transistors, or gate if the FETs, of these large ones, yeah? So between the base, let's take the fact they're probably going to be bipolar, for instance. Between the base and the emitter, you might have this coil connecting, you know, base to emitter effectively. And to AC, high frequency, that's a signal, but to DC, it's just a short circuit. So you may well see low resistances between some of the pins on these because of the coil, yeah, and it's not really a short. And the only way to find that out is to take this off. The other thing we haven't really checked is for short circuit diodes in the bridge rectifier, yeah? So we'll have a look at that as well. So your diodes are here, 1, 2, 3, 4, yeah? And this end, this is your AC input if you like, yeah, through the fuse. And I'm expecting this to read effectively like open circuit, yeah? From here to here, here to here. And I'm getting a bit of a resistance there, and that may not be normal. Let's look at these two. So the outside ends this is the positive or the negative, yeah, and I'll know because it goes to these big capacitors. So if we go from here to this capacitor, yeah, I can see that's the positive end of the capacitor, the negative end is marked, yeah. So these two is the positive end of the bridge rectifier, yeah. So that means these two is the negative end, goes to the negative end of the other capacitor, yeah, negative. So that's your plus and minus out. Let's have a look at the diodes. So that gives like a reading, and that's the diode junction. That gives a diode junction, and a kind of a reading. I'm not sure what I'm getting these readings. Diode junction, and a kind of a reading. Kind of a reading. Diode junction. So I'm pretty sure the diodes are okay. None of them are short, but I'm not quite sure why I'm getting this other reading when they reverse. I'd expect it to read open, to be honest. One other thing I've noticed on this, let me just zoom the camera right the way down so you can see it. I think this might have come out okay. I'm just looking at where this large capacitor, this one, solders to the board, yeah. And can you see around the pin? It looks like there's a halo, like a ring around Saturn. Can you see it? Just angle it a little bit, like a dark circle. Can you see around there? That might be a bad soldered joint, and that ring effectively might be a crack all the way around it. And that, if it is, could be something to do with why it went bang also. So what I will do is just solder that to be sure. Let me get the soldering iron on. One moment. Yeah, soldering iron going to standby, that's what it was. Yeah, so it's worth looking for this sort of thing, especially you'll find it where there's a large component soldered to the board, yeah? Because obviously, you know, when you're moving or knocking it around, vibration can cause them to fracture. This next one doesn't look too clever either, can you see it? So I'm going to just make sure these are well soldered. Okay, that's that one. And well matched, I might as well do the other two. They might have been okay, but they visibly look like they might not have been okay. I mean, sometimes it's obvious and you can actually see, it's broken, yeah. That was like, possibly. Okay, so we've done that, we've measured around this bridge rectifier, so I'm now going to remove this large heatsink with these main devices and I have another look around the bridge rectifier. So I'll just zoom out again a little bit and we'll get this unsoldered. So you can see there's 3 pins here, 1, 2, 3, 1, 2, 3, and then there's probably like a metal lug. Yeah, there's one here. There's probably one on the other end. Yeah, there's one on the other end there. So there's like 2 metal lugs as well, which hold the heatsink to the board. Yeah, you can see quite clearly one of the metal lugs is going to here. Was it going to here? I don't even know if that's going to AC. I suspect this heatsink is live, you know, when the thing's running. Doesn't surprise me. Doesn't surprise me. I think that's live when it's running. Okay, so let's get this off of here. What I'm doing is, have you also noticed, do you see that there? This copper track seems a bit damaged. Is that because a surge of current has gone through this track? It goes to one end of one of the main switching transistors, I think. No, it goes to the bridge rectifier. Positive. And I wonder if that's also, you know, showing you something that's a lot of power's gone down somewhere here. Yeah, it looks to me like that goes to the primary with the standby power supply, which is the one that's blown up. Yeah. Goes down there, and then the other end of the coil comes to the main, well, the only switching transistor for the standby. I think that's also been caused by what went wrong with this. Okay, so we've done enough Sherlock Holmes on this now. Let's unsolder some stuff, eh? Let's unsolder some stuff. Okay. Add some leaded solder first. to make life easier. I know I can use, if you see my videos, you know I've got a vacuum desoldering tool. But let's just try to do it the way, you know, if you guys are using more basic equipment, yeah. You know I can make this easy for myself, so I'm doing this for your benefit really, to show you how to do is with just basic kit. But if it gets too difficult, I'll use my my kit. I'll do it for your benefit to a point, yeah. But there comes a point when I say, Luke, buy one of these because this is what works better. Okay, so let's see if we can unsolder these things. It was looking very much like what's gone wrong with this is an explosion, effectively, in the standby. I wouldn't be surprised if these main transistors on the main side of the supply turn out to be okay, and that the low resistance was just due to the base drive coming through the transformer, or gate drive if they're MOSFETs. I wouldn't be surprised. Let's clear a bit of that stuff off there. No doubt we will find out. Looks like this PCB was designed to take a different device as well, which is why there's like an empty hole where there was nothing in it here. Either side of here there's like two other holes, so it's obviously they might use this PCB for a higher rated power supply and use different transistors. Then we can solder. Get rid of that crap. I've been asked what my solder wick is, by the way. It's this one, Chemtronics, yeah. Chemtronics size 4, yeah. People have asked me what it is I actually use, and that's the one. It's good stuff. It was recommended by a guy on Bad Caps forum when I wasn't having much joy with solder wick, and he recommended me this one, and now I use it all the time. A little bit more flux will help in the area of this one. Okay. Okay, I think I've got it. I think I've got it. Let's go for that one. Yeah, it looks good. So now it's just the little pegs that are holding this in place. Yeah. Skip forwards if you want, guys. While I just finish this job, but you know, sometimes I like to show you how to do this. So it looks like there's one here. This is kind of like a terminal post. Is it there? No, it's not there. It's here. The big thing. Yeah. Which proves, undoubtedly, the heatsink is connected to a live somewhere. Can we get this one off? Yes, with a bit of effort. It's looking fairly clean now. Okay, and then there'll be one more of these pillars on the heatsink at the other end. Look for the oval thing. Here it is. It's here. That big thing. And then this should come off with a a bit of effort and a bit of luck. Was that the right place? No, that isn't the right place. I think the peg's here. Yeah, I can see now it's like an oval. That's some resistor or something. The thing's here where the actual pillar is for the heatsink. Yeah, come on, come on, get with it. almost out of this roll. I buy these like 10 at a time, so they keep me going. Let's just get us a lug. Oh yeah, that's done. So hopefully now this thing will actually come out. Seems fairly tight at the moment, so what we need to do is figure out which of these pins is unsoldered and which one's not. Let me zoom the camera down. Yeah, so something isn't unsoldered at the moment. Easiest way is to kind of like push on the pins and see if they're free. See, that one is moving, yeah? This is one of the transistor legs. Let's see if these are actually free. No, that's not unsoldered. So now we can effectively just get the soldering iron and kind of like push it to one side usually. Yeah, you just be able to push it over a little bit. That's not, yeah, there we go. Other ones here. And just push it the other way a little bit. Yeah, that's moved. Oh, I see. The other one isn't actually unsoldered. It's there. Yeah, I see it now. Almost the end of this roll. Let's see it. Okay. That's free. So I should be able to move that now with the end of the tool. Yeah, move the leg. Yeah, moving. This one still isn't quite free. I think it might be now. Let's see if it moves. Yeah, it's free now. Yeah. So this is the next one. That's free. This one is free, and this one, I think the last one is still soldered. Yeah. So we'll get into that one. Take your time with this. You know, take your time with these things, guys. Don't rush at it. Yeah, just steady. You will get there. Okay. You will get there. Just take your time. Take your time. Do it right. Who sung that song? SOS Band, I think. Yeah, it was. Okay, that looks like it's unsoldered. That looks like it's probably unsoldered. So yeah, now it's coming, yeah? Now it's coming. Is there something else holding it in place? It's out, but there's just something holding it. Something else oh! Something else holding it. Yeah. Okay, we've got it. We've got it. I think you can see straight away that this has been charred. This is where this thing's gone bang, and this standby supply. If that's just flux or what it is, it looks a bit messy, yeah. So here's our little heatsink with 3 devices on it. What shall we see? Shall we see if any good? Let's see if any good. Let's use the little components analyzer. Okay, so I've got the components analyzer. Let's have a look if these are any good. I mean, basically we have 2 transistors which will be on the main power supply. You know, that generates the 5, the 12, and the 3.3, and then this one was generating the standby, the small power supply. So that's what we actually have. Let's see what these are like. I know I saw some low resistances around these, but considering the base, if it is bipolar, is being driven by a transformer, it might not be unusual to see like base emitter very low. Okay, that's an NPN silicon transistor, so it is bipolar, and it's a good one. That's a good transistor. What's the other one like? This looks like it's... No, it was just a bit of something. I thought it was discoloured, like it was been fried a little bit or something, but not. Okay. That's that one. Let's see what this one is. Short circuit blue, green. Right, okay. No shorts on the test leads. That's short circuit, blue green, and almost certainly for a bipolar transistor. This is the base, this is the collector, this is the emitter. Almost all power transistors of this type are that way round, and it's saying base emitter short. That effectively will stop this transistor from turning on. It wasn't short collector to emitter or collector to base, so it kind of doesn't put a short circuit on, you know, like the voltage coming in, but it just can't turn on. Basically, it's faulty. After all that, it's faulty, yeah. So that must have been one of them low resistances I could see. What's this one? What's this thing? Short circuit green blue. Okay, so this is short as well. This is the one that drives the standby. Okay, this is short. Green blue on this one was these two. Yeah. If this is a transistor, this would be base collector emitters. This would be collector emitter short. That would cause a short that would effectively blow the fuse. I'll show you that. If it's a FET, that's the drain, and this would be the that'd be the gate, and this would be the draining source. What part numbers are they? Let's have a look. MJE 13007A. Let's make a note of that one. And this one's a HNK60Z. Okay. Right, so I've got them, yeah. So that's what they are. Those MJEs, they're transistors. In fact, one's good, so we know the transistors. What's this other device? Let's just go over to the desktop and let's have a look in the web browser. Yeah, let's see if we can find the data sheet or something for that one. HNK. This sounds like a FET. That sounds like a sort of a FET data sheet. N channel 600 volts. Yeah, a high voltage FET. That's what you sort of expect to find on the switch mode. This is the thing. Yeah, it looks like ours. And ours was short between the middle leg and the right hand one, which I'm saying is drain and source almost certainly. Come on, give me a data sheet. You've already threatened you're going to do. Let's have one here. Let's have one. I'll just get this. Okay, after a couple of attempts, I've actually got a data sheet now. So there it is. So yeah, that looks like ours. And you can see pins 1, 2, 3. 1 is gate, 2 is the drain, and 3 is the source. And we've got a short circuit from drain to source. So that would blow the fuse. And I'll show you why. That would blow the fuse. Let's go over to the desktop again. Okay, let's get a bit of paper. Okay, a bit of dicky card, eh? A bit of dicky card. So, what we've got here basically, we're interested in the standby, yeah? Live neutral, yeah, coming in. And this goes via the fuse and the switch, yeah, to the bridge rectifier. Oh, AC, yeah. And coming out the bridge rectifier, we have plus, we have minus, about 300 volts, yeah, thereabouts. This will go to 2 capacitors in series, yeah. That's the two big capacitors you can see here. Obviously the bridge rectifier is the 4 diodes, yeah. But I'll just draw it diagrammatically like that, and I'll just twiddle that thing, because for some reason my camera never seems to want to stay in focus. So that's what we've got coming in, yeah. This point here, this is hot ground, yeah, effectively. So on here, this will go to the standby and to the main power supply, yeah. But the standby will have a transformer. We know it's a FET. It's either go directly to ground or it might go through a little resistor. But we'll put it to ground, yeah. And the transformer here is the output, that's your secondary. This is 5 volt standby. Once you have a rectifier diode and a smoothing capacitor, yeah. and possibly a voltage regulator. So that's what we got coming out of this. The FET is driven by pulse width modulation, PWM, which is an oscillator making square waves, yeah? And the width of the pulses will determine how much voltage comes out of this supply here. I'm sorry about this camera, guys, it's really annoying. So effectively, the wider the pulses, the wider the duty cycle, the more time the transistor's on in each cycle, yeah? So effectively you can have something like this, yeah? Or you could have, and this is, you know, fixed frequency, or you could have something like this. So they're all still the same frequency. You can just see that this is on for more time than it's off. This is off for more time than it's on, yeah? So that will give you a higher voltage and that will give you a lower voltage out, yeah? And that's what it does, it varies the pulses. So anyway, that's driving this, yeah? And that's pulsing this rapidly. So what's happened in our case is this here is short circuit, yeah? So you've now got, from the positive, 300 volts directly through the coil, shorted to the negative. That's a short, yeah? And that's what's happened, which is why it looks rather charred in that area. This begs a question, doesn't it now? If that's what's happened, yeah, and it is, because that was short, yeah, that is what's happened, why am I not seeing a short circuit between the positive and negative outputs of the bridge rectifier? I'm not. Look, this is the board, yeah. I've taken the transistor out now, fair enough. But when I checked before on the bridge rectifier, the diodes, the four diodes, where are you? You're over here. I went positive to negative, I didn't see a short. And that says I should have seen a short. So why? Well, one possibility is this transformer primary is actually burnt out by the massive current flowing down there. It's burnt out, so that's now open circuit. That has caused us not to see, yeah? So let's have a look at that. So I'll zoom in on the board a little bit. This is the bridge rectifier. So this is the positive output, both ends of this. Let me just put onto diode mode. Let's get the thing in this shot. Yeah, okay. So these two diodes, this is the positive end of the bridge rectifier. And if you notice, it goes through this bit here that looks like, why is it resist? Come on, it's got hot. So from positive, it goes through here, and this is the one end of the transformer coil, yeah? And then the other end of the transformer coil is here, so it's not open circuit, and that goes to the middle pin of the transistor. So that is, I've checked from here, we've got connection, this is reading a few ohms to there, so that's there, yeah? That's the middle pin on the transistor. This is the left, this is the right. So we know we've got the continuity there. So from the other end of the transistor, this end, I should have continuity back to the negative of the bridge rectifier. And I don't have. That's why I'm not seeing a short. Because, or 4 ohms, which is what the coil is reading. So I don't have a connection from there. So where's that go to? Well, it goes down here. It goes to something here, yeah? What is that anyway? That's the resistor. It goes to a resistor. So what we've actually got is what I mentioned before. We've got positive, yeah, primary of the transformer, yeah, FET, a resistor, yeah, negative, hot ground, and this goes to your bridge rectifier, yeah, that goes to here. So that's what we've actually got. And this is short, and that's okay. It's reading about 3.4 ohms. I say it's okay, it's not open circuit. So does this resistor go here, like I've drawn? It must go to here, which is the negative end of the bridge rectifier, yeah? So that's the resistor there, yeah? So let's have a look from the other end of this resistor. This end we know goes to the transistor. Let's get this in the shot. This end we know goes to the transistor, and the other end should go to the negative of the bridge rectifier, and it does. It does go there. So this resistor is basically open circuit. What's it reading? 3.2 kilo ohms. That's why we're not seeing a short, because of that resistor, but that should be a low value resistor, because the main current's flowing through the transformer is also flowing through this resistor, so it's got to be low value. And it's marked with a brown, green, silver, which brown, green is 1.5 and silver is effectively divided by 100. You can look up a resistor color code calculator. That's a 0.15 ohm resistor. Yeah, from the colours on it, that resistor there, 0.15 ohms. Yeah, 0.15 ohms, which makes sense. Yeah, and it's reading kilo ohms. So that's why we didn't see a short, because this resistor here, this resistor here is open circuit. It's open circuit, well, nearly. .2 kilo ohms. Yeah. 4.2 kilo ohms. So I can say from here to negative. Yeah. Also, interestingly, here, this is one end of the heatsink. Told you that heatsink was live, didn't I? I told you that heatsink's live. So that's why you shouldn't touch them things. Okay. So that's the first problem. Transistor blown, resistor open circuit, and all the current went through this primary this transformer, yeah? And it's possible that's fried as well. What might have happened to that? It's not open circuit, but you could have effectively, yeah, a short between two turns. Now if you know anything about transformers, you'll know that like the output voltage is a ratio between how many turns there are on the high voltage side and how many turns on the low voltage. So like effectively, like if it's got 10 times less turns than that, it'll give you 10 times less volts. So that's got 250 volts, and this has 10 times less turns, it'll have 25 volts, yeah? So you might think, well, what difference does it matter if one turn is short, because there might be like 1,000 turns, yeah? So if you've got 999 instead of 1,000, what's it matter? Yeah, well, it does matter, and what matters is effectively that shorted turn there means what you've got is this transformer, yeah, to your FET, yeah, plus volts. Your secondary, yeah, this is your 5 volt standby, yeah, and you've also got another secondary with one turn that's connected to a short circuit. So when this starts to work, it'll induce into this short-circuited turn like another secondary that's got short circuit load on it. So it'll put a massive current into that, and it won't work. Yeah, it'll blow the transistor again, basically, or the FET, because that one shorted turn destroys the inductance of the transformer. It's like it's got a massive load on it. Yeah, very low voltage because only one turn, but a huge current. Yeah, so that's why it matters. So that's what's wrong with it. But that's not all that's wrong with it. Yeah, that's what's wrong with it, but that's not all that's wrong with it. We've got a blown up capacitor here, so let's take that out. Let's get rid of this. Let's see what it is. Yeah, let's get the remnants of this thing out of here. So it looks like this is where the diode's soldered, and this is the capacitors here. Looks like these two pins, possibly. Yeah, I think it's here. Let's unsolder it. Let's see if we can get it out. See if these are the right legs. Yeah, a bit of solder on this one. It pushed in. I'm guessing that's the capacitor. If I just do that, that might actually make it fall out the board if I'm lucky. No, but it is coming out of the board. So let's get hold of this. Let's get hold of this thing and see if I can pull it out the board. Yeah. Well, no, I just pulled a piece off it. I didn't actually pull it out the board. So have another go. It's coming. It's definitely the right thing. Just need to. There we are. Alright, let's see what this thing is. So this is the remnants of an electrolytic capacitor. Yeah. You can see it's like 2 bits of foil, effectively, in a coil. Yeah. And that's what's left of that. Now that was a 50 volt capacitor, yeah? That used to be a 50 volt capacitor. And it's on the secondary of the transformer. So it's possible a lot of voltage also got down into here as well. I mean, if too much voltage got through the transformer, that would would go bang, yeah. I mean, more than 50 volts in here, it would go bang. Does that mean we've got a short circuit on from the primary to secondary on this transformer? That's one possibility. It's not so common, but you do sometimes find transformers short circuit primary to secondary. So let's have a look. So this is the primary side, where I see the 3.5 volts. Yeah. Let's see if that's the secondary. I should see completely open circuit, which I do. Right. So then that leads us to. Did it dry up and fail? Just get too hot and boil? But it looks burnt to me. That looks burnt, yeah. Was there some sort of massive surge on this side and this thing failed that caused that to blow? That seems possible. That's on the 5 volt standby rail, yeah. And a massive surge coming down here, if that's what happened, isn't going to be a good thing, because, okay, the 5 volt standby went to the computer, but we haven't got the motherboard. That's fair enough. But it also powers this chip, which drives the main transistors, which might, I mean, this kind of like, did that power surge do that and also cause the base of one of these transistors to go short circuit? Possibly. So what we have here is a bit of a mess. Is it worth doing anything with it? Well, from the point of view of repair, no. But from the point of view of learning something, well, yeah. So let's imagine this is actually a power supply that you need to repair, yeah. You've got 2 ways with this, really. One would be to try and repair this power supply, the 5 volt standby, yeah. So you have to either find the correct part or find an equivalent. You've then got quite a charred circuit board that might cause you a problem with high voltages on it. I'm not sure. You've got another little transistor down here. This will form an oscillator circuit, and that might be gone as well. You've got quite a bit of blackening on this side of it, yeah. You might have shorted turns on the primary, so it's never going to work again anyway, because you can't replace the transformer. But there is another way. There is another way, and that would be to effectively bypass this, yeah. Take the transformer out, just so there's no high voltage flowing into this circuit, yeah. Take that out. Get a little 5 volt power pack that's physically small enough to fit inside the ATX case, yeah. And use that 5 volt power pack to drive from the output of this diode into the 5 volt standby, and power this chip and power the 5 volt standby. So effectively, rather than the expense of getting the bits and God knows what else might be wrong with this. So there's a resistor gone as well, we know that. We know there's also a resistor open circuit, this one. So you can get like a 5 volt power. You might have one line around 5 volt 2 amps, probably £2 or £3. So we could do that, and we could literally get the thing to fit inside it, because quite a lot of room in this ATX case. If it was like a power supply, you know, like a big expensive one, and you couldn't afford to replace it and you can't get the bits, you could do that effectively, put the 5 volt power supply outside of it and just feed the 5 volts in to replace this standby circuit. And if this chip's good, and the transistors driving the main transformer is good and everything else is good, it'll work, yeah. Can we prove this is a good chip? Well, yeah, we can, because what we can do is, we know the 5 volts are coming on this diode, yeah, use the purple wire. What if we get our bench power supply and put 5 volts on here to ground and use our bench power supply to power 5 volts into this? If we take an oscilloscope, because I can't think of any other particular way of doing it, and get a data sheet for this chip, if we see this driving pulses into this middle transformer, then we know this is running, and all we've got to do is replace one of those MJE thingy bobs, bipolar transistors, and it should work, yeah. So, you think that's a plan or what? Do you reckon that's a plan? Let's have a look and see what this chip actually is. I'll get the magnifier and see if I can tell you what it is. It is a W. I'm going to take the other side up. It's a well trend, it says on it. WT 7520. WT 7520. Let's see if we find the data sheet for that one. Yeah, found the data sheet for that. So this is it, WT 7520. PC power supply pulse width modulator, supervisor, controller, pulse width modulator, power supply controller. Yeah, that's what it is. This is the pin out, and we can see these are the pins. So we have VCC. This is your power coming in, P for power type, power supply voltage. Yeah, and it tells us if we look down here, VCC is 5.5 volts. That's probably a maximum, yeah. Then we have outputs C1 and C2, yeah. Pulse width modulation, open drain outputs 1 and 2. Okay, so those are your outputs from the chip. So I'm assuming these have some sort of pull-up resistor or something on these outputs, because they're open drain, and with a bit of luck, we might be able to see if this thing's actually working by sticking the 5 volts into it and see what we get coming out of it. So that's that. We can get these cheap enough. I mean, you get like 5 of them for 90 cents. With 59, yeah, so like 149 including the postage. I can get 5 of them. I can get 10 as well. 10 for 150. A bit more postage. That's probably, yeah. That'll probably do me. What was this guy? Yeah, it's 144 and 120. Yeah, I can get 5. I can get 10. So they're not expensive to buy either. So yeah, I think it's well worth us now having a look to see if we can actually do something with this. Let's go back into the overhead camera. I'm here. Okay. So we can try this. Yeah, we can get our power supply here. Let me just check first that this diode isn't short-circuited to ground or anything stupid like that, yeah? Because this way I'm going to inject the voltage, yeah? So let's just be sure. Otherwise, all that happens is the bench power supply just go over current. So this is the diode here. Let me put it onto voltage range and see what I've got. It's probably a Schottky diode, so it might be like 0.1. That's low, that's well low. That suggests there's also some more problems with this. Okay, don't worry about that. We'll unsolder one end of this diode and we'll stick the 5 volts in where 5 volts should go, yeah? What's 5 volts standby to ground reading? Another interesting thing. This is 5 volt standby. Okay. What's that reading to ground? Here's a meter. What's 5 volt standby reading to ground? Oh, only 50 ohms. Oh, okay. Thought it might be a bit more than that, but that's not a lot. It's like 100 milliamps or something at 5 volts. Okay, let's take this diode out, yeah, and now let's see what we've got now. Okay, so here's our diode. It's not too hot anymore. It's not a bloody hot. Okay, diode range. Let's see how this is reading. That reads open. Yeah, that checks okay. I'll just get it on again. Yeah, it's a Schottky diode as well, 0.12. So we know that's okay. So we can stick our 5 volts in here. Yeah, I'll solder one leg of the diode back in, make it easy. We can stick our 5 volts in there, yeah, and to ground, and we can see what happens, and we can see if this chip is running, yeah, and if we've got 5 volts standby on the purple wire. And if we have, then we know we can definitely bypass this rather than try and fix it, yeah, and we can hopefully get this working by changing the one transistor. Okay, so I'll solder this on and I'll connect my bench power supply. Okay, so that's ready to go. So I've got the power supply set to 5.2, that's close enough. It's connected via a little switch here, I can switch on or off, yeah. You can see the thing here, and then the negative I've got connected to one of the black wires on the ATX power connector. Yeah, here. This is also connecting my ground from my oscilloscope as well. So what we can do is first is clip the 5 volts onto here from the power supply, yeah, and switch it on, and let's see what happens. Well, it draws about 100 milliamps. No, it's about 10 milliamps. It's not really drawing anything. Let's see if we've got any voltage here. Yeah, it jumps up off the screen. So yeah, there's 5 volts there. See on the oscilloscope, yeah, we've got voltage there. Have we got any voltage on the chip itself? 16, 15, 4, pin 13, yeah. No, I don't see any voltage getting to the actual oscillator chip. Ah, I see why, because the bloody resistors fell out. The diodes fell out. Let me remake that connection. I'll just solder it. Yeah, I think you can see what had happened there. So when I soldered one leg of the diode in, it effectively broke the track, supporting the weight of the diode. So I've just put a bit of wire in there now just to link it to where it should go. So that's 5 volts coming in. Let's switch it on again and see what we get now. Right, 110. The 10, by the way, is the little LED on my switch here. So it's drawing 100 milliamps. Chip is not getting hot. Let's see if we got any voltage on this chip now. I'll use the oscilloscope. If you see the trace jump upwards, then you'll see I've got 5 volts. I think it's set to like 1 volt per division, yeah. Yeah, so that's power on there. Is it running? No. Why is it not running? Because you have to get the green wire to ground, yeah. You have to get the green wire to ground for this to switch on. So, let's do that. Easiest place to do it is actually on the ATX connector itself. I'll just do that. Okay, so I've now poked another bit of wire, actually a little resistor on a bit of wire, just a low value resistor from the green wire to ground. So this should now activate when I switch it on, yeah? See what happens. Still 100 milliamps, okay? Let's see now if we have any supply voltage. Got my oscilloscope probe all caught up in the wiring now. So, pin 13, oops, I've lost the ground. I've lost my ground connection, too many bits of wire stuffed in too many holes here. Okay, let's have a look. Yes, that's got 5 volts. And this still has nothing. So, this chip isn't running, yeah? It's fairly obvious this chip isn't running. It has supply. We can just check on the data sheet to see where the enable pin is, make sure it's low. One moment. Yeah, we can see on the data sheet then that we have power good on pin 11. So pin 11 high should mean power good, low means power fail. So that should be high on pin 11, yeah? And the enable will be on one of the other pins. Let's see. This one, remote on off. low means it's turned on and high means it's turned off. This is your green wire. So your green wire is on 9, we can look at that, and power good is on 11, and we can look at that, yeah? And 9 we expect to be low, 0 volts, and 11 we expect to be high, if it's actually running, yeah? So let's have a look to see what's there. Okay, so we're still drawing 110 milliamps. So pin 9 should be power good, and that should be low. And yes, look on my oscilloscope. That's low, yes, that's good, that's low. Pin 11, power good, should be high. That's also low. So this chip has power, but it's not working. It's got power, it's enabled on the green wire, but it don't work. And that's hardly surprising considering the voltage has come down into here. So we now have more problems. This is dead as well. Is it worth it? Is it worth me bothering? It'd be interesting to see. We have 3 more transistors here, and we have a couple more diodes in here, yeah? So if we just check those, let me just zoom it in. Yeah, I think it'd be interesting to see if we've got any anything else down here that looks short. I mean, I think if all the diodes and transistors in this area look good, I think it'd be fun to get some of these, get a transistor, and see if we can actually make this work by bypassing all this and using just a 5 volt 2 amp supply to power the the purple wire, the 5 volt standby. I mean, it's not surprising with that capacitor blown. There's probably a lot of voltage coming down here and probably blowing a few other things. So just keep this focus on this, yeah. So if it's blown anything else, it's going to be diodes and transistors, yeah. So let's put the meter on. You can see it, yeah. So we're in diode test mode. So let's have a look at all the diodes we can see down here in transistors. There's one here. That reads okay. Because this chip was 5.5 volts maximum, it wouldn't take much to blow that, yeah. That one looks okay. There's another diode up here. What's this one like? Whereas these diodes are probably much more tolerant to a higher voltage, yeah, without committing heavy carry. I'm probably happy with that one. And then we have a few transistors. So one of them's here. One of them's here. Can we see them from the other side? Not easily. I'll zoom it out a little bit so you can see the meter as well. In fact, no, let's set the meter where you can see it. One moment. Right, you can't see me anymore, but you can see the meter. I've now got all the meter bleeds all tangled up, yeah. Okay, so let's see if we can actually check these transistors. So one of them's here. If I get onto the 3 legs, I might be able to just see if it looks okay. Yeah, that's like a diode junction. Yeah, that was like 2 diode junctions. That's probably okay. I mean, without going directly into details, there's another diode right next to this. That was the diode. I'll look the other way on the diode. Yeah, that means okay. There's another diode here. Yeah, that seems okay. So there's another transistor in front of the one I was actually just testing. Let's see if we can get onto this one. You can't see it easily, but it's down under here. That means like a diode junction. Can't find the other one. Let's try from the other way. A diode junction. We've got one here as well. Yeah. So that means like it looks like it's an okay transistor. There's 2 more. One here. If it is a transistor, not a voltage regulator. And that reads like a transistor. That reads pretty much okay. There's another diode up under here. That reads okay. And the last one. Let's just get to this last one. Yeah. Yeah. Okay. So it's looking like now something's gone wrong here Yeah, this is blown, and somehow too much voltage has got into here. It's blown this capacitor, exploded, and it's blown the chip that drives the main transistors. So if we get some of these chips, we get like 10 for like €1.50, and the transistors are a similar price. I'll get a few of each because they're useful for parts for future use. Yeah, and we'll try with this one to, as I say, bypass all this circuit. We'll get a little 5 volts 12 volt supply and see if we can get this oscillator working. If we get this oscillator to work, then we'll replace the 2 power transistors, stick it together and see if it runs. Okay guys, hope you enjoyed that. A bit in depth, but I think it was a very interesting one, and I'll see you soon on another video, and in a few weeks we'll be back to see what we can do with this one. Let's see you soon now guys. Ciao.